Michael Faraday discovered the law of electromagnetic induction, which says that a changing magnetic field can produce an electric current in a nearby wire. So in this simulation, I've got a magnet, and I'm going to show the field lines around the magnet. When I take the magnet and I pass it through one of these wire coils, then not only does it turn the light on, but it also makes the voltage, the voltmeter, show a reading. And if I take the magnet and I send it through twice as many loops, I get twice as much voltage. If the magnet is not moving, however, I don't get any voltage. And this is what it means that the magnetic field has to be changing. The wire coil has to experience a changing magnetic field. And the way that I can do that is by passing the magnet through so that the number of field lines intercepting the coil is changing, or the area of those field lines intersecting the coil is changing. The other thing that I could do is I could switch the poles of the magnet by clicking here. And every time I do that, I also induce current, and I can see a voltage reading here, because this also counts as changing the magnetic field. I'm not changing the shape of the magnetic field, I'm just changing the direction of the magnetic field. And in fact, this is one of the most dramatic ways that I can induce a voltage in the wire. So again, this is the law of electromagnetic induction, which states that a changing magnetic field can produce an electric current in a nearby wire. All right, I've got a solenoid here, just a coil of wire and an empty space in the middle. I've got an old school ammeter that measures in milliamps, so very small amounts of current. And here I've got a magnet on the end of this pole, and I'm going to, this is a neodymium, I'm going to push the magnet inside the coil, and the coil is going to experience a changing magnetic field. Check out that ammeter when I move the magnet through the coil. So this changing magnetic field is inducing current in the coil as evidenced by a change on the ammeter. I have a giant cloud magnet here, north pole on top, south pole on the bottom. I have a giant coil of wire here. You can see the coil is going around the perimeter of this plastic ring. And this coil is now connected through these wires to this ammeter, which is going to measure any current that's flowing through the coil. If I put the coil through this magnet, the coil is going to experience a changing magnetic field, and watch that ammeter for evidence of current. Notice it only moves if the coil is moving, right? Because the coil has to experience a changing magnetic field. This is a hand crank generator. It generates electricity by having you turn a crank, which spins a coil. You can see the coil in there. And the coil is connected to an LED light right here. Now if you spin it as is, the light doesn't turn on. But if you add a couple of ceramic magnets above the coil right here, now the coil, as it spins, will experience a changing magnetic field. It's going to go in and out of the field lines generated from this permanent magnet. And if you look here at the red LED, I can generate electricity. That's electromagnetic induction. A fan is simply a very small motor. When it's connected to electricity, current flows down the wires through a coil, a very small coil on the inside of the fan, which is surrounded by some magnets. The coil rotates and it causes the blades of the fan to spin. But can a fan become a generator? Well, yeah, if I spin the fan blades, I can push current the other way and generate electricity. Take a look. Watch the ammeter here for very small amounts of current when I blow through the fan. can see the needle deflecting as I've turned my fan into a generator. A microphone is simply a backward speaker. This is how microphones work. So I've taken an old speaker and cut it, removed the paper diaphragm off the front, and behind it you can see the voice coil inside. The voice coil is attached by these wires to the two contacts on the back. This causes a speaker to vibrate when you connect it to a power supply, such as your phone. But if I take a new speaker and connect it to a very sensitive ammeter, this measures in microamps, which is millionths of an amp. And then I tap on the speaker, you can see that I generate very small amounts of current every time I push on it. And this is exactly what you do when you tap on a microphone and you say, testing, testing, 1, 2, 3. Is this thing on? All that a microphone does is it takes the vibrations that are produced by your voice as you sing into it, and it amplifies it so that instead of producing microamps, it produces enough current that can then be pushed out some speakers and you can hear somebody really, really loud. A microphone is just a backwards speaker. This is electromagnetic induction at work. What's the difference between a generator and a motor? Well, a generator starts with mechanical energy and it converts it to electrical energy. If I connect this to a light, I can convert it to electrical energy. A motor, on the other hand, converts electrical energy into mechanical energy. So if I connect this now to a battery, I start with electrical energy, that's the input, and the output is mechanical energy. So is this a generator or is it a motor? It depends on how you connect it. What if I connect two of these together? I'm going to clip their alligator wires so they meet in the middle. And now, if I turn this one, causes the other one to move. This one is inputting mechanical energy from me and outputting electrical energy through the wire. This one is inputting electrical energy and outputting mechanical energy. So in this case, this one that I turn is the generator. The one that's being turned is the motor. Similarly, you can take one of these and connect it to a fan. And as I turn this crank, the fan moves. So I've got, in this case, this is the generator, and this fan is acting like a motor, because this is receiving my mechanical energy, producing electrical energy down the wire. This fan is receiving electrical energy and converting it into mechanical energy. This flashlight nicely illustrates the principle of electromagnetic induction. As I shake it, it produces light. How does it do that? Well, if I look on the inside, I see a wire coil, and then I see a magnet that slides back and forth as I shake it. So every time I shake it, I'm moving the magnet through the coil. As a result, the coil experiences a changing magnetic field, and current is induced in the coil, which turns on the flashlight.